Right, so we're going to go through topic 1 in GCSE chemistry, right? And we'll start up here with this thing here, periodic table of elements. Now, this is something we're going to go through in a bit more detail in a future topic, right? But we are going to focus on elements today as well. So this is what the periodic table looks like. You've seen this before probably, and you'll have it in the back of your exam paper when you sit your GCSE exam. Now, going down the periodic table is where you have your groups. And going across the table, so this way, is where you have your periods, right? So you've seen groups and periods before. So going down, so group 1, group 2, that's a group. You've got this kind of gap in the middle, group 3, group 4, group 5, and so on and so on. Now going across the table is where you have your periods. So periods go across, whereas groups go down, right? Now the periodic table is where you find your elements. And this thing here is an example. So if we look at what an element is, right? Elements, we've just seen plenty here, right? They're all over the periodic table. The periodic table is just where elements are found. Now, this thing here, we just draw out like a random thing. Let's just use X, right? On a simple level, this is just a random thing. We'll look at a specific example in a second too. But on a simple level, all an element is a letter with 2 numbers and a box around it. So we've got our letters in the middle, right? This is a symbol. This would tell us what element it actually is, right? We've got these 2 numbers, and one of them is a mass number. One of them is called the atomic number, right? And now we'll look at which one's which in a specific example. So again, a simple level, an element is just a letter with 2 numbers and a little box drawn around it, yeah? That's all an element is. That's what we're saying for now. Now, if we take a specific example, let's say like sodium, for example, right? So sodium on the periodic table will look like this. You've got Na, 23, and 11. So again, this thing here is our symbol. It tells us what element it is. So it tells us, this Na tells us that it's sodium, right? And again, we've got a mass number and the atomic number. Now, to recognize which one's which, right? Now, on your periodic table, like this one that you'd get in the exam, the mass numbers are at the top. So sodium's up here, right? So the mass number 23 is at the top. So that's our mass number. But another way to kind of remember this, another way to think of this, right, is that the mass number is always the bigger number. So between 23 and 11, 23 is bigger than 11, right? That's our mass number then. It's the bigger one. So the mass number is the bigger number. So the one we're left with, the smaller one, is our atomic number. And we'll look at in a second what this thing means, right? But that's what an element looks like. Now, we're going to kind of go through this in order of size. And what I mean by that is we've started with an element. And we're going to look at what elements are made out of, what happens if you join elements together. Now, if you join 2 or more elements together, you'll get what's called a compound, right? So again, by definition, a compound, all a compound is 2 or more elements joined together. So an example of a compound is like KBr, for example. So potassium bromide. If you went looking for this on the periodic table, right? If you went looking for KBr, you wouldn't be able to find it. But you could find potassium and you could find bromine. Again, compound, what we said it was earlier, is just 2 or more elements joined together. So 2 or more elements chemically, now that's important, 2 or more elements chemically joined together. So again, you wouldn't be able to find a compound like KBr or like H2O. So you wouldn't be able to find it on on the periodic table. But look, we can find potassium, it's right here, and bromine right here. We've just joined 2 elements together to make a compound. That's all a compound is, right? So again, going in order of size, elements, if you join them together, 2 or more elements together, you get a compound. Now, an element itself is made out of 2 or more of the same atom. So what we're saying is like this sodium here, for example, it's only made out of sodium atoms. It's nothing else, right? So that's made out of sodium atoms. Now, atoms are something that we'll look at as well, right? But they're really, really small things. Now, atoms make up all substances. They're the smallest part of an element that exists, right? So they make up everything. But now, what are atoms made out of? And again, you can see here how it's going in order of size. An atom makes up an element. Elements make up compounds. Now, atoms are made out of what we call subatomic subatomic particles. Now, subatomic particles, it does sound a little harder than it needs to be, or harder than it needs to sound, right? So, subatomic particles, all that's meant by this, so sub just means part, right? Atomic, like, of an atom, so parts of an atom, right? These things make up an atom. Atoms make up elements, elements make up compounds. We're going to look at all of these now. Now, examples of subatomic particles, the three that you need to know of are protons, neutrons, and electrons. So these are three things that you'll find in an atom. So protons, neutrons, electrons make up an atom, right? Now, we're going to look a little bit at this now. So this thing here shows the structure of an atom. Now, this is like a general atom, right? Just like, you know, a random one. And we'll look at specific examples of these two. So like we said before, elements are made out of atoms. So if we look over here, now, in the middle of an atom, we said earlier that atoms, right, contain these three things: protons, neutrons, electrons. But where are these on this structure? So on this diagram, we'll label them, right? In the center of an atom, we have what's called the nucleus, right? And we're looking at where these three things are located. Now, in the nucleus, we have our protons and our neutrons, right? And we're going to come back to a bit more about these in a second, right? So in the nucleus of an atom, in the center, we've got protons and neutrons. Now, these circles around it, right? These circles are what we call shells. And this is where our electrons are found. So electrons are located on these shells, right? So protons and neutrons are found in the nucleus, in the middle of an atom. Electrons are shown by little crosses like this on these shells. Now, there's a rule here. And the rule, you probably heard it before, is 2, 8, 8. And all this really tells us, all this really means, right, is the number of electrons that fit on each shell. So the maximum number of electrons that can fit on the shell, the first shell is 2. It can't take any more than that, right? The next is 8. And it follows this format. So the first shell can only hold a maximum of 2 electrons. The next one can hold 8. The one after that is 8. And it follows this structure. So 2 on the first shell. It can hold 8 on the next one. And just to do this real quick, right? 8 on the last one. This is the maximum that it can hold, right? So just as a generalized approach, this is what an atom looks like, right? 288 is our configuration, and we've got a nucleus in the middle. Now, if we look at a specific example, and we'll come on how to do this in a second, right? We'll look at how to do sodium, the configuration of sodium. Now, I've used that word configuration here, right? Don't let it confuse you. When we talk about electronic configuration or electron configuration, all we're really saying is like how many on each shell. Don't overcomplicate this shit, yeah? If there's anything you're confused about, just either rewatch parts that you need to, DM me and get a one-to-one little video with me, or a one-to-one call. We'll go through something, or just have a look at the questions after this on the video. Now, right, sodium, 2311. Now, let's look at what this is again. So this is an element of sodium, right? We said the mass number is the bigger number. The atomic number, the one we're left with, the smaller one, would be this 11, right? Now, let's look at what the mass number actually tells us. Now, the mass number, the bigger one, tells us the number of protons and neutrons in this element. That's what that is. That's why that's there, right? The mass number tells us the protons and neutrons. The atomic number lets us know the number of protons and electrons. Obviously, in your exam, you'd write the full words out here, right? I've just kind of shortened it here. But mass number tells us the protons and neutrons, and the atomic number tells us the number of protons and electrons. Now, using this information, we can figure out the number of protons, neutrons, and electrons in this sodium. And this is how you do it, right? And again, this is quite straightforward, but it doesn't matter which element they give you on this periodic table. It's the same working out every single time. The only thing that changes are the numbers, right? So again, the atomic number tells us the protons and electrons. So if we want to know how many protons and electrons are in sodium, we literally just look at this number and copy it. So if that's 11, and the protons are 11, the electrons are 11. And it's as easy as that to find out how many protons and electrons are in this thing, right? Now, for neutrons, it's a little bit different. We just find the difference between them. So the difference between the mass number and atomic, we do 23 take away 11, and that gives us 12. And that's how you find the number of protons, neutrons, and electrons, right? If we look at like real quick another example of this, right? Just down here, we'll take like carbon for example, right? So carbon on the periodic table, if you went to find it, it'd look a little something like this. So carbon, C, 12 and 6. Here's our symbol to let us know it's carbon. Here's our mass number. Here's our atomic number. Now, again, if we wanted to see the number of protons, neutrons, and electrons in this carbon element, this is how we do it, right? In an atom of carbon, this is how many of these things we have, right? So again, the atomic number tells us the number of protons and electrons. We can just copy that one down. The mass number tells us the protons and neutrons. To find out the neutrons, it's the difference between them. So 12 take away 6 is 6 as well. And that's how we do this every single time. The reason we do that for the neutrons, well, we said earlier the mass number, we treat this like it's maths, right? The mass number tells us the protons and neutrons, right? So if we know here that big number, that mass number is 12, and we know that there's 6 protons because, well, the bottom number tells us there's 6. We're thinking to ourselves, to find the neutrons, well, what do we add to 6 to get to 12? Then it must be 6 as well, right? So again, to find the neutrons is just the difference between the mass number and the atomic number. Do 12 take away 6, and it'll tell you the neutrons, right? And there'll be a few more like this on the questions later on. You can give them a go. But that's how you identify the number of protons, neutrons, and electrons in an atom of an element. So now we'll take a look at actually showing this on an atom and what this looks like, right? So again, the structure of an atom is what we did earlier. We've got this 2A8. This tells us how many electrons can fit on each shell. So there's a maximum of 2 in the first shell, then there's 8, and then there's 8. And in the middle, we have our nucleus that has our protons and neutrons, right? So if we're drawing the atom of sodium now, right? Really, when you're showing an atom, you will get asked this. This is quite commonly asked in like exams, but like for exam questions, they love this shit, right? But you rarely have to show the nucleus in the middle. You won't have to show the nucleus. It's just really understanding that it's there. But what we will have to show is the electrons. Now, you know how to find how many electrons are in a thing now, right? Just look at the small number, the atomic number. So we know now that there's 11 electrons in sodium. And really what we're going to look to do is fill these electrons on these shells, on these circles, in this order of 2A8. And we're going to do this until we run out of electrons, right? So let me show you what I mean by that. So on the first shell, we know it can only hold a maximum of 2 electrons. And sodium only has 11. So if you used up 2, we know we've got 9 left. The next shell can hold a maximum of 8. So 1, 2, 3, 4, 5, 6, 7, 8. We've used up 8. We've taken 8 away from 9. We've got 1 electron left. So there's 1 in the last shell. And we've finished with all our electrons. So the configuration of sodium, again, configuration, don't let it confuse you. All it means is really how much are on each shell, how many electrons are on each cell, right? So there was 2 on the first shell, there's 2 here, 8 on the next one, so 2, 8, and then 1, just 1 electron in the last shell. So that's our configuration of sodium, and that's how you do this, right? If we were to like do the same for carbon here, we'll just do another example, right? So we know the electrons, the number of electrons to be 6 now. So showing this on like an atom, right? We've got these circles, these shells, it looks a bit wonky, but we've got 6 electrons in total in carbon. Because again, we just look at that smaller number, the atomic number, right? There's 6 electrons and we fill it up in the order of 2A8 until we run out of electrons. So the first shell can only hold 2. So again, we've used up 2 from 6, we've got 4 left. The last shell, 1, 2, 3, 4. We've used up all our electrons. So the configuration of carbon now is 2 and then 4 in the next shell. So 2 in the first shell, 4 in the next. And that's how you do these, right? Again, if you're confused about any point, just look over this video, right? Rewind or just ask me for help via DM, school app. Now, right, that's how you do this. Now, this is something, we're going to look at the periodic table in more detail in another lesson, right? But you can tell using the configuration what group and period that this element will be in. Now remember, groups go down, so down group 1, down group 2. Periods go across, so these are our periods, right? Right, so the group that an element's in. Now, I'll take a note of this, right? So elements, Elements are grouped based on the number of electrons on the outer shell. So I'll take note of this again. Elements are grouped based on the number of electrons on the outer shell. And again, this sounds a little harder than it needs to sound, right? It's harder than it needs to be. So electrons are grouped based on the number of electrons on the outer shell. So this thing here, what we just drew out, this carbon, we had 6 electrons in total. We figured the configuration to be 2 and then 4. So on the outer shell, on the last shell of this thing, this one here, we've got 4 electrons. So that tells us carbon's in group 4. Sodium up here had 1 electron in its last shell. So on its outer shell, on its last shell, it has 1 electron. So it must be in group 1. If we look at the periodic table up here, I've made a bit of a mess of this. Let me just start rubbing some things out. But we can see sodium just right here. So sodium's over here, right? So in group 1, because it has 1 electron in its last shell, everything else in group 1, so lithium, potassium, rubidium, these all will have 1 electron on the last shell. Carbon's over here in group 4, because it had 4 electrons in its last shell. If we do another example, just for the sake of it, right, just real quick, nitrogen, for example. So we got nitrogen, 14, 7. If we wanted to see again how many protons, neutrons, electrons there are, we follow the same thing that we did earlier, right? So this number, the atomic number, tells us the protons and electrons are 7. We just copy that number, right? We don't need to work anything out here, we just copy that. The neutrons, the difference between, so 14 take away 7 is 7 too. So if we drew this out, right, again, we've got 7 electrons in total. So we've got 7 electrons, 2 go in the first shell, we've used up 2, we've got 5 left. So 1, 2, 3, 4, 5. So 2 and then 5 is our configuration. So there's 5 on the outer shell, so it must be in group 5. Oh wait, it is, right? So again, elements are grouped based on how many electrons are on the outer shell. So if it's in group 1, it's got 1 in its outer shell. If it's in group 3, for example, it's got 3 electrons in its last shell. If it's in group 7, it's got 7 on its last or outer shell. Makes sense, right? Now, the periods. So that's how you tell what group they're in. Remember, groups go down. The period that an element's in depends on the actual number of shells. So how many shells do you actually have, right? So here, we've got 2 shells. 1, 2, just 2 circles here, right? So it's in period 2. Here, we've got 3 shells. 3 shells in total, 3 of these circles, right? So sodium is in period 3. And that's how we kind of figure that one out, right? Okay, cool. So again, if you're confused about any point, anything that we've done so far, just rewind if you need to, right? Rewatch this as many times as you need, or ask me a question whenever. I can take like a little video for you and go over something, or jump on a call with you or something like that to help you out here. So again, what we've said earlier is that atoms are made, so atoms are composed of our protons, neutrons, and electrons. I'm just not writing the full thing just to save us a bit of time here, right? But these are what atoms are made out of. You've got protons and neutrons in the nucleus, again, electrons on our circles and our shells around it. Now, we're going to look at this a little bit more now. So about our protons, our neutrons, and electrons, and what really we need to know about these things. So protons, neutrons, electrons. The 2 things that we're going to look at is the mass of these, so like how heavy they are, and the charge. Now, we're going to look a little bit more at charge later on also. But all I mean by a charge is whether something's positive or negative. That's all a charge is, right? So the mass of a proton, it has a mass of 1. Neutrons also have a mass of 1. Electrons have a mass of 1 over 1835. Now, you can tell just from looking at this shit that, well, electrons are very small, right? They're very small compared to the other ones. So these are 1 over 1835. That's tiny, right? So really, an example, you could even say just that they're very small. You need the idea that electrons are small, and electrons orbit the nucleus, right? These tiny things. Now, the charge of these, so talking about whether they're positive or negative, right? Protons are positively charged. So you've got P for proton, P for plus, P for positive. Neutrons, so P for proton, P for plus, right? Neutrons are neutral. They don't have a charge. So P for proton, P for plus, P for positive, right? Neutron, neutral. Electrons are negative now. I couldn't really think of anything for this one, right? But this is one that you'll see most commonly. like you'll see this in other topics too, right? Electrons are negatively charged. Now, these three things are made up in the atom as well. You need to be able to like know these and recall these, right? The mass and the charge, and same in exams what they are. So you can see from here though, just like we said, protons and neutrons have a mass of 1, electrons 1 over 1835. These two are a lot heavier. These two are the heaviest, right? And they're both found in the nucleus. So the nucleus, like we said earlier, is where our protons and our neutrons lie. So really in an atom, most of the mass is concentrated in the nucleus. It's the heaviest part because, well, electrons are really light and they're on the outside. They orbit the shells, right? But in the nucleus, we've got our two heavy things, our protons and our neutrons. So in the nucleus, we'll add to this, right? We'll say most of the mass is concentrated in the nucleus. That's just where most of the mass of it is, right? Now, the nucleus also has a positive charge. And the reason for this is, well, protons are positive, neutrons are neutral. So let's say, just for example, they had one of each, right? You've got a positive thing and a zero thing, a plus thing and a neutral thing, right? So overall, it's going to be positive. So the nucleus in the center is positively charged and these electrons are negative. We're going to come back to that idea later on. But again, this is everything you need to know for now about protons, neutrons, and electrons. Now, this is what we know the atom to kind of look like now. This is what we call the modern version of the atom, right? I'm going to talk about how that changed over time and the discoveries that were made to kind of get to that point. Now, first, right, the first kind of thing that the atoms look like. So what we're going to look at now as like a little subheading, we'll just call this the development of the atom. We're going to talk about what we know the atom to be and how it changed over time, right? So in terms of the development of the atom, atoms were first thought, so I'll get this down right, atoms were thought to be tiny spheres that couldn't be divided, right? So thought to be tiny spheres that can't be divided. So just tiny spheres that you can't break, but that can't be divided, right? So we're going to really look at how we went from this, just a tiny sphere, to this, how it changed over time. You can see a big difference between them, right? We're going to talk about the changes that were made to get to that point. So again, first we thought atoms were tiny spheres that can't be divided. Now, next we kind of discovered, so next is the discovery of the electrons. And really here we have our plum pudding model. And you might have seen this in a few exam questions. I know there's one on the worksheet that we're going to go through the exam questions in the next video, right? But the plum pudding model just essentially just looks like a plum pudding, right? It looks like this. So you've got a circle with a big plus in the middle and these negative electrons just embedded around, so embedded in there. That's the plum pudding model, right? We've kind of just taken this, whacked a plus in the middle and put electrons in there, right? But if we're going to put this into words, if we're going to describe this in words, right? Really the plum pudding model was just a ball of positive charge. So you've got a big plus in the middle. It's a big positive ball, but with negative electrons just kind of there, negative electrons embedded. Now, you kind of accepted that there's electrons that exist here, right? But a common question you get asked is comparing like these older models of the atom with the current model of the atom. If we look at this one, for example, and the modern one, there's a big difference between them. Now we know that the center, like we said earlier, the center of the atom is the nucleus, right? And that's positively charged because of our protons. Whereas in this one down here, oops, it's more further away than I thought. This one down here, it's just positive, like the whole thing is positive rather than the nucleus just being the positive part, right? The full thing is a positive ball. And you've got these electrons just kind of all over the place embedded there, right? Like it says here. But now we know the electrons are arranged on shells and them circles around it. Now, these are the kind of differences you'd be expected to say, right? There's also no neutrons here. Now we know that there's neutrons, but we'll get to that point. But again, we started off just thinking that there were spheres that can't be divided, and now we've got the plum pudding model of an atom. And you've probably heard of what came next, the alpha particle scattering experiment. So the alpha particle scattering experiment. So this is just kind of what it sounds like, right? So what they did here, the whole point of this, right, what they concluded, what they got from this. So this made a conclusion that the mass of an atom, so the mass of an atom was concentrated at the center. So concentrated at the center of the atom. So we know now that the protons and neutrons, the heavy parts, the ones with the biggest mass of 1, right, are in the middle. Even they are small, just bear that in mind. They're just a lot bigger than an electron. Don't mean that they're big, but most of the mass is in the middle, in that nucleus. And this kind of proved that, right? That's at the center. Now, they had a beam of alpha particles and they aimed it at gold foil, right? And they wanted to see how it would get through. Now, some emerged at different angles, some came straight back. Now, really, you're throwing these alpha particles at the center, so at this atom, so that it kind of like you threw these positive charge things to another positive charge thing in the middle, right? And they came bouncing right back. Why would that happen? Because positive things repel, right? So the positively charged alpha particles were scattered and thrown here, and they bounced straight back. And that kind of told them, hang on, there's a small concentration of positive charge in the middle, and that's our nucleus, right? So positive alpha particles were thrown at the atom. At the center, they bounced back. It came straight back, and that kind of told us that the nucleus was positive as well, right? Next came the Bohr model, right? So Neil Bohr, and what this dude kind of added to this, right, was that again we're slowly getting closer to the modern atom. We got this circle, now we got, there's a positive there. Now we're like, okay, there's a nucleus in the middle instead of the whole thing being positive. Now we figured that there was electrons with the plum pudding, but Neil Bohr kind of added to this, right? And he suggested, so this Bohr guy, right, suggested that electrons orbit the nucleus at distances. So just talking about them being on shells, right? So electrons are orbited at specific distances. So electrons are just arranged, not kind of scattered all over the place like suggested here, but on shells now, just orbiting around, moving around it, right? Now, later experiments shown that the positive charge of the nucleus can be subdivided. So you can break them down, right? Whereas at the start, we thought it can't be divided. Now, last, we've got James Chadwick. This shit's kind of long here, but you do have to learn this. You have to be able to compare them with the modern atom, but also know how it changed over time. So how we went from this ball, now electrons are here. We thought, shit, the whole thing's positive. Now we're like, okay, it's not all positive. The nucleus is positive, right? Now we've got electrons that are on shells, just located on these circles. Now Chadwick came up with, or provided evidence for neutrons. So provided evidence to show the existence of neutrons. So now we've kind of completed the whole thing, right? He's kind of shown that neutrons exist. And we've got to our modern version of the atom. If you have any questions about this, or if you want to watch over this again, feel free. If you have any questions, just let me know, DM me, right? Right. Now, this is pretty much everything about atoms and elements that we need to know of, right? We're going to look at ions and what ions are. Now, ions are just things that have they're either positively or negatively charged. Again, charge, we said this earlier, right, to be whether something's positive or negative, right? And this is all ions are, and you will have seen these before. So ions are things that are just positively or negatively charged, right? Now, if we look at this, let's take carbon, for example. You got carbon 12 and 6, and we list out, like earlier, the protons, neutrons, and electrons in this thing, right? How would we do this again? Just for the sake of it, you probably know how to do this by now. That smaller number, the atomic number, we literally just copy that for the protons and electrons. So if that's 6, then this is 6 and that's 6. But the neutrons is just the difference between them. So 12 take away 6 is 6 as well. So that's how you do that, happy days. But you've seen things like carbon. Now, actually, I'll come on to that in a second. But you've seen things like C plus or something like that. Something with a positive sign. Now, this thing is an ion because now we're positively charged. Right, that's all an ion is. So you've got C plus, you can have C minus, you can have C2 plus, C3 minus, there's all sorts, right? We're going to talk about what these are, what they mean, and hopefully this should make sense, right? Now, right, elements, all the elements that, you know, we had up here on the periodic table way back when. So all these things don't have a charge. You can see it here anyways. It's not like a plus or minus anywhere. They're all uncharged, right? And the reason for that is, like, every time that we've drawn these protons, neutrons, electrons out, every time we've looked at this, right, we've seen that the protons are the same as the electrons, because remember, we just copy that small number for both of them. So the number of them are the same, right? So the number of positive things that we have is the same as the number of negative things. So we've got 6 positive things and 6 negative things. They cancel each other out, right? So overall, there's a charge of 0. There's not more positive things or more negative things. It's uncharged, right? That's what an ion is. That's the difference with ions. We've either got more positive things, more negative things. We'll look at how this works, right? So again, let's just look at the protons, neutrons, electrons of this thing. And we'll do that for each of them, right? We'll look at the protons, neutrons, and electrons. Again here, protons, neutrons, electrons. Now, C plus, how does this different? How is this differ, right? So really with each of these, the only thing that's changing for these are the electrons. Everything else basically stays the same. So again, if these two were 6 here, everything else is just a 6. The only thing that's changing are the number of electrons. So we can just keep these the same, right? Now, C plus, we'll start here. This one has become more positive, right? And how do you become more positive? The way that, well, ions, the reason why they're more positive is because they've lost a negative thing. And that negative thing that they lose are these electrons. So we've got a negative electron, right? That's been taken away. So the way I usually teach this in person, and this sounds kind of stupid, right? But it should make sense. Let's say you had a group of really bad, negative, toxic friends, right? Just bear with me. Sounds stupid as hell, but it makes sense. So you've got 6 friends that are really toxic. So 1, 2, just real quick, 3, 4, 5, and 6. Oops. You know, these people are quite bad people for you. Toxic, yeah, sad faces. So 6 negative friends. Now, let's say we got rid of one of these friends. You know, you lose one friend from the friendship group. Now you've got 5 negative friends. It's better than having 6, right? So you're still negative, but you're more positive than you were before because you've lost one of them. So you started off with 6 negative things. Now you've got 5. And it's the same idea here. You become more positive by losing one. So in carbon, traditionally, normally, right, like we had above, you've got 6 electrons in carbon. But if you become more positive, you've lost a negative electron, a negative thing, right? So instead of 6, you've got 5 now. I'm hoping this makes sense. Yeah, just watch over that again if you need to. And there'll be some questions on the videos anyways, to practice anyways, linked to this. So C minus, how does this different? Now, with this one, we're becoming more negative than we were before. So again, usually, normally with carbon, we've got 6 electrons, right? But now we become more negative by 1. So we're adding a negative electron in. We're adding a negative. This stuff confuses a lot of students. So again, if you have any questions, if you need any more help, just let me know for anything, right? So you've got 6 electrons normally, but you're becoming more negative. So now we've got 7 electrons. It's become more negative by 1. A lot of students get confused with this because really there's a plus sign. They think they're adding things on, but really you're taking something away. And with chemistry, you'll see this a lot. It's like the symbols mean the opposite thing. So a negative means really you're adding things on because really we're adding on a negative electron. Positive means you're taking things away. It sounds the opposite of what it would normally be, right? In maths or something, but the positive means you're losing a negative electron. That's how it becomes more positive, by losing a negative thing, right? Now, if we take a look over here, it's the same idea, right? So traditionally, normally we start with 6 on carbon. So there's 6 electrons on carbon normally, right? And we become more positive by 2 this time. So we become positive by losing negative things. So now instead of 6, we've got 4 electrons. We've lost 2 electrons, right? Like again, we had 6 negative friends. You want to think of it like this: you've lost 2, you've got 4 now. It's more positive than it was before. Now C3 minus. You started off with 6 normally, but you're becoming more negative by 3. We're adding 3 more negative electrons. So now we've got 9 of them. This is how you work with ions, and it's the same for all. The working out is the same for all of them. The only thing that really changes are the numbers. right? The way that you do this is the same all the time. So we've looked at elements, we've looked at ions. Now, last one, let's look at isotopes and what these are. Now, we need to be able to define what an isotope is. You'll see plenty of these questions on the exam question walkthrough videos, right? But you need to be able to define, to say what an isotope is, and we'll go through the word for word definition of this, right? There's a kind of maths part involved as well, and I'll show you what it is just to help you understand it too, right? So isotopes, what these are. So what you'd have to say for this as a definition, the atoms of the same element, with the same number of protons atoms of the same elements have the same number of protons but a different number of neutrons. Don't let this confuse you. I'll show you an example of this now, right? But we've said here they're just atoms of the same element have the same number of protons but different neutrons. Atoms of the same element, same protons, different neutrons. Now, these two, carbon-12 and carbon-13, are examples of isotopes of each other, right? Now, we missed out the atomic number here, but you probably will see this in a few questions where it looks like this. But what you'd have to do instead is just put it in yourself, right? Just, if you wanted to, if you needed to, right? Just look at the periodic table. Again, you'll have it in the back of the exam anyways, and just fill that in. So let's list out, like we've been doing, you're probably bored of this by now, right? The protons, neutrons, electrons of each of these things, right? So again, smaller number, the atomic number, we can just copy that down. So 6, that tells us the protons, electrons, neutrons, the difference between, so 12 take away 6 is 6 as well. Now here, we've got 6 here, 6. Now, difference between, for neutrons, 13 take away 6 this time is 7. We've got 13 take away 6. Now, you should be able to see here that these are both atoms of the same element. We've got basically two types of carbon here. They're both carbons, but they're different kinds. We've got carbon-12, carbon-13. So they're both atoms of carbon. They're atoms of the same element. They have the same number of protons as each other, so the protons are the same, but the neutrons are different. So this is just kind of an example of this, right? So atoms of the same element, they have the same protons as each other, it's just the neutrons are different. And that explains why the mass numbers are different, because remember, mass number tells us protons and neutrons, right? Now, linked to this, we have something called the relative atomic mass. And this is where there's a little maths calculation involved, right? And you'll see plenty of these questions in the exam question pack after this, the walkthroughs after this, right? Now, the maths part to this, if you don't like maths, it should be fine still, right? These come up really often, literally almost every year, right? As either a 2 or 3 mark question. And the working out is quite simple, it's quite basic, right? Literally it's the same thing, it's the same working out every single year, right? The numbers are always, the only thing that changes is the numbers, right? The working out is always the same. And it's an easy 3 marks, it's the easiest 3 mark you'll get, right? Now, we'll look at an example of this kind of question. So with the maths part for this, right, this is the type of question that you usually get. And again, it's usually worth 2 or 3 marks, but again, it comes up quite a lot. It's an easy 2 or 3 marks when it comes up, right? It's something you don't want to get wrong. Now, here we've got these things written in the table. They can show this information in a graph, they can just write out in words, it doesn't matter how, but we've got a table that gives us the mass number and the abundance, so how much of that thing that there is, right? And here we've got gallium as an example. So we've got gallium 69 and gallium 71. These are 2 different types of gallium, the same way that we had carbon-12 and carbon-13, yeah? Now, really what it's saying is here that, so that's the mass numbers of them, that's how much of it there is. So there's 60% of gallium-69, there's 40% of gallium-71, right? Now, in terms of how to work this out, it's quite straightforward. Again, the working out is always the same. What you've got to do is here, you times these 2 numbers together, and then you add them to the next 2 times together, divided by the total abundance. Now, that sounds harder than it is, right? But literally, you could whack this into your calculator all at once and get the answer. It's quite straightforward. So like we said there, we times the first two numbers together. So we do 69 times by 60, right? So times them first two numbers together. So 69 times by 60. Times them together, then add the next two times together. So 71 times 40. Divided by the total. Now you'll notice here that the total 60 and 40 adds up to 100. And that's the case every single time, right, on these questions. So times the first two numbers together, add them to the next two. Just do this until you run out of things to do this with, right? So times them two numbers together, added to the next two, divided by 100. That's it. You can whack this into your calculator all at once. Now, an important thing to notice is that a lot of these questions, not all, but a lot of them will ask you to round to one decimal place or something as such. So that's the last mark point. Usually if it's a 3 marker, that's the last mark point, right? So once you get your answer, round it to one decimal place. We should get 69.8. Now your answer should somewhat be around these two numbers. So it should be somewhere close to 69 and 71. If you get an answer like, I don't know, 2 million or some shit like that, you know you've gone wrong somewhere. It should be somewhere close to, in between 69 and 71. That's how you do this. Again, just times them first two numbers together like we've done here. We did 69 times by 60, added to the next two times together. So 71 times 40, divided by 100. You can plug this into your calculator all at once. Now, like we said before, they could give you this information on a table, like they've done here, right? Or they can give it on a graph, but it doesn't matter how they give this information to you. It's the same working out every single time. So let's say you have the mass numbers at the bottom, so 69. And the abundance is on the y-axis, right? So 69 goes up, might go up to like 60, for example. And then 71 goes up to 40. It's the same working out. It's the same thing, right? So this graph looks stupid as hell. We do 69 times by 60, added to the next two times together. So 71 times 40. And divide by the total abundance, 100. Right, so times the same thing we done here, times the first two numbers together, added to the next two times together, divided by 100. And that's how you do this. That's how you work out the relative atomic mass, right? That's the calculation part that we talked about earlier. It's quite straightforward, and it's the same thing every single time, right? Now, there's a definition for this too. We need to be able to define what is meant by the relative atomic mass. What actually does this mean? So relative atomic mass. The way to work it out, as in terms of a calculation, is just what we did above, right? That's how you'd answer these kind of questions. But relative atomic mass, in terms of like a definition for it, it's the weighted, so the average weighted mass of an atom. And again, this sounds quite wordy, just don't overcomplicate this, right? The average weighted mass of an atom, compared to, so the average weighted mass of an atom of an element, right? So sorry, atom of an element, because remember we're looking at a certain element here, like gallium here, for example, right? So the average weighted mass of an atom of an element compared to 1/12 of the mass of carbon-12. So you're taking the average mass of an atom and comparing it to a 1/12 of carbon, the normal carbon that you see, right? This is just a definition that you need to know and, you could get asked this and you could say it like that, right? But this is basically the full first topic in paper 1 chemistry, AQA. Now, if you've got any questions about this, if there's anything that you need, just ask at any point, or just rewatch any points, rewatch as many times as you need to, really. But these kind of questions come up on the first few pages of the chemistry exam. Now, these are questions you don't really want to get wrong. They're easy marks to pick up on, and they usually do give quite a few marks in these, right? So again, don't get these wrong. Don't waste marks in the easy part of the paper. The questions that we have linked to this, the next video, and the walkthroughs, the exam question walkthroughs, there's plenty of exam questions for you there to try, and the exam video walkthroughs as well. So try the question, watch the video, see if you got it right. Now, with that, with chemistry, there's only so many ways they can ask you the same thing. There's only so many ways they ask you the same question. It gets really repetitive. Once you've done enough questions, you'll realize it's literally the same answer quite a lot of the times, and they do repeat a lot. So the more questions we do with chemistry, 3, the higher your grade will be. So yeah, just have a go at them questions, apply what you've learned here. If there's anything you need, any help you need, just drop me a DM or just let me know.